Welcome back to this course on pulse width modulation for power electronic converters. So far we have covered a few modules. Let us just take a quick look at what are the various modules we have covered here. So, first we had an overview of power electronic converters. So, in this overview of power electronic converters, we looked at various things like we started from switches and we looked at DC-DC converters like buck converter, boost converter, etc. And finally, we came to voltage source converters and current source converters and covered multi-level converters, etc. So, from here we picked up this voltage source converters. I mean with particular emphasis, we have been particularly emphasizing on 3-phase voltage source converters, and we discussed various applications of voltage source converter. Like one application for example is motor drive, which is what we have been which is again a focus here area here. You can also look at active front end converters or power factor corrected compensated rectification, and they are also used as voltage source converters. They are also used for harmonic compensation and reactive current compensation, etc. So, we had an overview of various power electronic converters, and we also looked at various voltage source, the applications of voltage source converters. And these two topics, I would say the first two topics, they actually are actually more subject material of other courses. We covered a part of this only to establish very good fundamentals over power electronic converters before we launched onto pulse width modulation. And in the subsequent module we launched onto pulse width modulation. It's called purpose of pulse width modulation. Why we do that? Now, if you take a voltage source converter, the voltage source converter has a DC voltage on one side and it requires the AC voltage on the other side. So, the purpose of the pulse width modulation is to make sure that you can control the fundamental voltage. That is one of the purpose of the fundamental thing. And the other reason that you need to do is, other than the fundamental voltage which you desire, there are also harmonic voltages that get generated, and these harmonic voltages have to be mitigated, they have to be reduced to some extent if not eliminated totally. And these harmonic voltages also have certain adverse effects, they like extra heating and pulsating torque and so on and so forth. We will have to try and mitigate those adverse effects of these harmonics, and that is what we would call as purpose of pulse width modulation, essentially twofold: to control the fundamental voltage and to mitigate the harmonics and its bad effects. And from that point we looked at pulse width modulation at low switching frequency. We considered the situation when the voltage source inverter switches at a low frequency. Now, why? Firstly, actually this was very relevant in relevant a few decades back, when the switch is available, the power semiconductor device is available, could not switch at very high frequencies, they switched at rather low frequencies now, like something like 400-500 hertz kind of frequencies now. But the modern devices switch at much higher frequencies. Nevertheless, this is still relevant in certain contexts such as high power drives. This low switching frequency is really, what we mean here is, the ratio of switching frequency to modulation frequency is low. So, in high power drives you still have situations where the switching frequency could be very low, because the power levels are very high and the devices really still can't switch at very high frequency. Further, you have the other application which are high speed applications. Your switching frequency may be quite high, it may be like 10 to 15 kilohertz, but the modulation frequency itself could be something like 1.5 kilohertz, 1 kilohertz, 1.5 kilohertz, a little higher than that. So, that happens in high speed drives, and when in such kind of cases the ratio of switching frequency to fundamental frequency is low, and once again this becomes relevant. And what I would say is, rather than the relevance of this to the present context, this has more value to us from a learning point of view. It is very important, it is a very useful step to go through this, to learn how to control fundamental voltage and how to handle the harmonics, which are the two what you would call as the purposes of or objectives of pulse width modulation. It is actually the low switching frequency gives us a very good opportunity to learn that, and that is the reason why we went through that. We looked at a single switching angle. With one switching angle we could control the fundamental voltage. With two switching angles we learned how exactly to handle the fundamental, how to maintain the fundamental voltage and also handle the harmonic voltages. So, what we would like to say that is, actually it is for us, we did this exercise for us to realize that there are several options available. For example, you have a voltage source inverter and you want to produce about 80% fundamental voltage. Now, the fundamental voltage should be 80% of the square wave fundamental voltage. So, firstly what we do as a result of that exercise, we realize that there are several possibilities, there are several options are available for you to produce that 80% fundamental voltage. Several sets of switching angles can give you that. So, first there are several options, and then what are those options, and then how to evaluate those options. For example, if you want 80% fundamental voltage with only 2 switching angles, you can look at eliminating fifth harmonic as one possibility, or you can make sure that fifth and seventh harmonics both are low, that is another possibility, or you can try and make sure that the pulsating torque, let us say the sixth harmonic pulsating torque is low, like this. So, you can evaluate different options that are available and you can go in for these low switching frequency. That was the reason why we went through the step of pulse width modulation at low switching frequency, and from this point we are going to what is currently more relevant, which is the triangle comparison based PWM. You take a practical inverter. Now, most of the inverters are likely to be switched with something like sine triangle PWM or some variant of sine triangle PWM, and this is a very common way of doing this, and this is what we have been dealing with over the last 3 lectures, and today would be the concluding lecture of this particular module on triangle comparison based PWM. So, let us see a little more on what is this now. So, as part of this triangle comparison based PWM, we have been looking at 3 phase inverter. All that we saw earlier was we looked at sinusoidal PWM. We looked at sinusoidal PWM for both single phase as well as 3 phase inverters, and we also looked at third harmonic injection and bus clamping PWM. I can say that all these like sinusoidal PWM, third harmonic injection, bus clamping PWM are all specific cases of triangle comparison based PWM now. So, today we would just consolidate our understanding of this and try to generalize all this and get consolidate our understanding on triangle comparison based PWM. So, this lecture is going to specifically focus on triangle comparison based pulse width modulation for 3 phase inverter, right. So, now what is a 3 phase inverter? Just a quick recap. We know that there are 3 legs corresponding to every phase, and each leg is a single pole double throw switch. This is pole, this can be connected either to the top throw or to the bottom throw. Similarly, all these poles are there now, and a voltage source inverter, this is how you can draw that using generic switches, and if you were to realize with IGBTs, this is how you can realize. So, everything is a bidirectional switch, as we have talked about several times earlier in this course, and these 2 switches, the top and the bottom switches in each leg switch in a complementary fashion now. So, as we have mentioned before, there are certain redundancies which are available in this voltage source inverter. So, what is that redundancy? A 3 phase load can be shorted either by having all 3 top devices on or all the bottom devices on. If you look at here, now let us say all the top devices are on, it shorts R, Y and B, that load is getting shorted, or keep all the top devices on and all the bottom devices are bottom devices can be on with the top devices being off. Once again R, Y and B are shorted. Thus, the load can be shorted in 2 different ways, either having all the top devices on or all the bottom devices on. So, in space vector terms, I am throwing a new term at you called space vector, which we will be actually starting to deal with from the next lecture onwards, but I am taking the liberty of throwing this term at you a little prematurely. So, what is that? This is actually what do you mean by space vector is a transformation. There is a transformation called space vector transformation, which we will discuss in the next lecture, and the space vector transformation transforms 3 phase voltages into a 2-dimensional vector, 2-dimensional voltage vector. Now, what exactly is this transformation? We will discuss it in the next class, but right now you take it from me that, or many of you may already be also aware of this, if the 3 phase voltages are all 0, then the corresponding voltage vector is a null vector, that is what we can say. So, then you take it from me. So, this null vector can be applied using 2 different states, that is one state is where all the top devices are on and the other state is where all the bottom devices are on. So, essentially these are equivalent statements. I am just saying that you can short the load by keeping all the top devices on or the bottom devices on. So, this corresponds to one state, this corresponds to another state, they are called 0 states. These are 0 states because there is no power flow between the DC side and the AC side during these states, and the load is fully shorted and the energy is simply freewheeling there. And so, in space vector terms, it is just a different terminology, and so and in space vector terms what you are doing is you are applying a null vector. You can say that you are applying a null vector rather than saying that you are shorting the load, and this is just an alternative statement now, right. So, it is another way of saying that is you can add a common mode component to the 3 phase sine waves. You have 3 phase sine waves and you can add some common mode component to the 3 phase sine waves now, and this common mode component should consist of triplet frequency components. So, we have seen some examples of this earlier. One of the first examples we saw was a third harmonic frequency can be added. If your fundamental is 50 hertz, your modulation frequency is 50 hertz, you can add a 150 hertz component, a small amplitude to the 3 phase sine waves. That is one example. We also saw certain other examples of common mode components in the previous lecture on bus clamping PWM. So, today in this lecture we would try to gain a better understanding of this particular thing that we are talking about, right. So, let us just say that since I said triangle comparison based PWM, let us try and define that. What is this triangle comparison based PWM? It is one way of generating PWM waveforms. PWM waveforms are the gating signal waveforms that are required to switch the devices on and off. So, how do you do that? This method involves comparison of 3 phase modulating signals. What you have is, you have 3 phase modulating signals, whatever is maybe a signal, there is a particular modulating signal for a particular phase that may be shifted by 120 degrees to get the modulating signal for the next phase, and yet another 120 degree to get for the signal for the third phase. So, you have a 3 phase modulating signals, and these 3 phase modulating signals could be sine, that is what is most commonly used, I mean it is many times used, but not necessarily so. It could be something else other than sine also. So, you have 3 phase modulating signals each of them corresponding to each phase, and you compare these 3 phase modulating signals against a common triangular carrier. This is what you do for in triangle comparison based PWM. So, the triangle comparison gets its name from the carrier being triangular and the modulating signals are compared against a triangular carrier now. Now, what do? You compare when the top device is on, when the modulating signal is greater than the carriers. The modulating signal is either greater than the carrier or it is less than the carrier. If the modulating signal is greater, then the top device is on. If the modulating signal is lower, then the bottom device is on. So, this is what you do, and in very simple terms, this is a description, this is a very simple description of what is triangle comparison based PWM. Now, you have the simplest case of 3 phase modulating signals is 3 phase sinusoidal wave. As you can see, this is the R phase sinusoidal wave, and the yellow phase I am just using green for better visibility, and then this is what you have the blue phase signal, right. So, you have RYB, the 3 phase things. These are compared against a common triangular carrier, and they would produce the PWM signals or the gating signals for the 3 legs of the inverter. Excuse me. So, now we would talk in terms of the average voltage in the 3 phase inverter with sinusoidal modulation. We are considering sinusoidal modulation now. So, what do you mean by sinusoidal modulation? We have 3 phase sine waves as we just saw in the last slide now. I am just describing all this mathematically. What is that? Let our 3 phase signals, I would call them as MR, I can call them as MY, I can call them as MB. And what is MR? I would say it is Vm sin omega t, and this omega is the modulation frequency, and that is 2 pi f. If f is 50 hertz, it is 2 pi into 50 radians per second, that is what omega is. So, it is Vm sin omega t, where Vm is the amplitude now, and the modulating signal for Y phase is Vm sin omega t minus 120 degree, and you can see that this is shifted in time by 120 degrees, or 1/3 of the carriers, I mean of the line cycle, of the fundamental cycle. And the B phase modulating signal is the same waveform shifted by another 120 degrees. Instead of 120, it is now 240 now. So, it is Vm sin of omega t minus 240 degrees now. So, this MR, My, Mb is just the mathematical description of the 3 sine waves we just saw here now. So, this is the mathematical description of these 3 now. So, what do we do now, right. So, this is the modulating signal. Let us look at what is the so called average pole voltage. Let us break it up. Say pole. What is pole? Pole is nothing but the midpoint of a leg, because we said every leg is a single pole double throw switch, and pole means midpoint of that. The terminals R, Y and B can be called as poles. Now, let us say R, the voltage at R is measured with respect to O. So, what is O? O is the DC bus midpoint. And now, what is VRO? Let us look at the instantaneous value. If the R phase top device is on, then VRO will be equal to this VDC by 2. Its top device is on. When R phase bottom device is on, then this VRO instantaneous voltage, I am not talking about average yet, the instantaneous will be equal to minus VDC by 2. Now, what are we doing? In one half carrier cycle, we are having the top device on for a while and the bottom device on for a while. So, sometimes it is plus VDC by 2 and sometimes it is minus VDC by 2, and your average voltage will be somewhere between plus VDC by 2 and minus VDC by 2, and this is what it is now. So, whatever is the modulating signal value in that half carrier cycle divided by the peak of the triangular carrier, MR by Vp times VDC by 2. Let us take MR is equal to Vp, which is the highest value it can have during linear modulation if you are not going into over modulation. Even if you are going into over modulation, any value in excess of MR is just ignored anyway. So, this is the highest value that we can look at is Vp now. If it is Vp, then what do you have? VRO average is nothing but VDC by 2. The average pole voltage is equal to plus VDC by 2. If MR is equal to minus Vp, then the average pole voltage is equal to minus VDC by 2. So, for any value of MR which is between minus Vp and plus Vp, you will get some average pole voltage which is between minus VDC by 2 and plus VDC by 2. The idea of average pole voltage is something that we have been carrying through from the time we discussed buck converter. Again, you have an average pole voltage. In the case of buck converter, the average pole voltage is constant at steady state. It is equal to the average output voltage now. On the other hand, we are talking of DC to AC conversion here. So, the voltage at the pole is sinusoidal quantity. This VRO average is proportional to MR, MR is a sinusoidal quantity, therefore, VRO average is a sinusoidal quantity. And what about VIO? VIO is also a sinusoidal quantity, and it has the same amplitude as MR, or the other R phase voltage excuse me, has the same voltage that, but it is shifted in phase by 120 degrees now. And once again you have VBO which is further shifted by another 120 degrees. So, you have 3 phase average pole voltages, and you can see that these two are simply scaled versions of one another. MR and VRO average are just there is what is there as a scale factor, and what is that scale factor? It is VDC by 2 Vp. So, you can look at the inverter simply as a gain. The simplest model or the 0th model of an inverter would be just a gain, and the gain is equal to VDC upon 2 Vp, where VDC is the DC bus voltage and Vp is the peak of the triangular carrier. And remember, we are using a bipolar carrier. So, the peaks are plus Vp and minus Vp here. So, that is what is your inverter's gain now. So, you have VRO average and VIO and VBO average. What are these? These are average pole voltages. What do you mean by that? The instantaneous pole voltage has been averaged over a half carrier cycle. That is what we mean by VRO average now. Right, these are the average pole voltages. These are measured with respect to the DC midpoint O. Now, what do we do next? Let us say we have VRY average is the average line to line voltage. Now, what is average line to line voltage? This VRY average is VRO average minus VYO average. It is very simple. If you take the instantaneous quantity VRY is equal to VRO minus VYO, right. So, the same way VRY average is equal to VRO average minus VYO average. You subtract those two quantities, you get VRY average. Now, the first quantity is sinusoidal, the second quantity is also sinusoidal, and they are the same frequency, they only have a phase difference. So, you will get another sinusoidal quantity of the same frequency VRY average, but its amplitude will be root 3 times the amplitude of VRO average. That is what you will have now. Now, let us say we have a 3 phase load. Let us consider a 3 phase star connected load. Let us say our motor is there, and this motor itself is, let us say there is a 3 phase winding like this. Let us say this is R phase terminal, this is terminal Y, this is terminal B, and this is the neutral point. This neutral N is the load neutral, and this is different from the DC midpoint O. So, if you want to find out what is VRN average, if the load is balanced, then what you can do is VRN average is 1/3 of VRY average minus VBR average. And so, if you substitute all these values one into the other, you will find that VRN average is equal to simply Vm by Vp times sin omega t VDC by 2, and that would be same as VRO average itself. This is a special case when you are talking of sinusoidal modulation, your VRN average will be equal to VRO average, whereas when you start injecting common mode, then this will no longer be equal, as we will just see in the next slide now. So, in the case of sinusoidal modulation, you are using 3 phase sinusoidal signals, your average pole voltages are sinusoidal, and the average line to line voltages, which are the differences between the average pole voltages, they are again sinusoidal, and the average load phase to neutral voltages are once again sinusoidal, and the load phase to neutral voltage VRN average is same as VRO average is what you want to see. In fact, this is the idea behind sinusoidal modulation. Now, you want to apply, let us say VRN average and VYN average, you want this to be sinusoidal. If you want this to be sinusoidal, you have to make sure that this VRY average and VBR average, VYB average have to be sinusoidal. If you want that, then what you can do is, if you simply ensure that VRO average is sine and VYO average is sine, then the difference between the two will also be sine. So, you can modulate VRO average, VYO average and VBO average such that they are all sinusoidal of the same amplitude, and they have a phase difference of 120 degree. You can do that. That is the basic idea between sinusoidal modulation. If you want your VRO average to be sinusoidal, have your MR to be sinusoidal now. So, let us just look at the next level of complication here of the next step of adding a common mode voltage now. Now, once again we are looking at average pole voltages now with common mode added now. Let us we start from the same 3 phase sinusoidal signals Vm sin omega t, Vm sin omega t minus 120 and we excuse me, Vm sin omega t minus 240. These are 3 phase voltages now. So, these are the same voltages. This is what is the desired fundamental voltage. These are measures of the desired fundamental voltage now. Now, you take the liberty of adding some amount of common mode voltage now. Today, we are trying to gain better understanding of what is this, what could be a suitable value of common mode voltage. You can't add anything arbitrary that you want. We have some examples at least which could be common mode voltages. We just want to do a little more of this now, right. So, we are adding that, and MR plus MCM is MR star. Similarly, My plus MCM is My star, MB plus MCM is MB star. So, these are 3 phase modulating signals with common mode added into them. That is what you have now. So, now what is going to be a VRO average? Your VRO average is not MR times VDC by 2 VP, but it is MR star. You look at this MR star, and what is this MR star? It is MR plus MCM. So, VRO average is no longer sinusoidal. It is proportional to MR star, which is not sinusoidal really. It is sine plus some common mode component added to that now. So, your VRO average is is proportional to MR star, VYO average is proportional to My star, VBO average is proportional to MB star, and this factor VDC by 2 VP can be taken as the gain of the inverter. That is what it is. Now, what do you get for VRY average? Is VRO average minus VYO average. Something interesting happens here. What is that? When you subtract VRO average minus VYO average, what you are essentially doing is you are subtracting MR star and My star. And what is MR star? It is MR plus MCM and My plus MCM. So, if you subtract MR star minus My star, the MCM in both of them, the common mode voltage gets cancelled. MR star minus My star is simply the same as MR minus My. So, the common mode vanishes. Though VRO average is non-sinusoidal, VRY average is still sinusoidal, because the common mode components in both VRO average and VYO average get subtracted, because they are common mode. It is the same thing that is there. This has been added to all the 3 phases, and so they get added, they get subtracted from the line plane voltages now. So, VRY average, VYB average and VBR average, the 3 phase line plane voltages are sinusoidal. There is no common mode component in this, right. So, you can add common mode component to the modulating signal, and you can get away with that, and it will not appear in the line plane voltages now. So, what happens now? VRN average is the same thing, 1/3 of VRY average minus VBR average. Again, this is assuming that the load is balanced. So, this simply comes from KVL again. If you take VRN average, what is your VRN average? Now, VRN average will be equal to Vm sin omega t by Vp into Vdc by 2, which is not the same as VRO average. VRN average is actually equal to this MR divided by Vp into Vdc by 2, whereas VRO average is MR star into Vdc by 2 Vp, and MR star is non-sinusoidal, VRO average is non-sinusoidal, whereas VRN average is sinusoidal now. So, this is what happens when you add common mode to your 3 phase modulating signals now, and one very simple example of common mode is third harmonic injection, which we have already seen now. So, you can see that this R phase is shown, the R phase signal is shown in dotted lines, red color dotted lines. The yellow phase is sine wave is shown in the green color dotted lines, and the B phase sine wave is shown in the blue color dotted lines now. You add a common mode component, and what is this common mode component? That is a small 150 hertz component, like what is shown here in dashed lines. This is added to all the 3 sinusoidal signals. So, your R phase signal, for example, is now like this now. So, what happens? The peak value comes down. That is, whenever the R phase sine has its peak, the common mode component, when the R phase has a positive peak, the common mode component has a negative peak. So, it brings down the total value now. So, it is something like its head is bent down a little. So, you are passing through a door, and the door height is not very high, the door frame height is not very high. So, you just gently bend your head and you get into that. This happens in many old buildings in India. So, like that the head is slightly bent here, and so you can do this now. So, what you can do effectively is, you can see the peak value of the MR star has come down, as I pointed out earlier. So, the peak value can go as high as the peak value of the carrier, and therefore, this gives, this is able to pack a higher amount of fundamental voltage, and that is why it gives higher DC bus utilization, as I pointed out earlier now. So, this is now one example that what I am showing of a possible common mode component. This has only a 50 hertz component, as I said before, and this is your MR, and your VR and average will be proportional to this, and this solid line is your MR star, and your VRO average will be proportional to this. Then let us look at this third harmonic injection, just put it all mathematically, whatever we have been seeing before. You have start with the same 3 phase signals MR, MY and MB, these are sinusoidal signals, and you add a common mode MCM to all the 3 to get MR star, MY star and MB star, right. Now, the common mode is a third harmonic sine wave, and therefore, I am saying sin 3 omega t, and what is its amplitude? I am calling it some KVM, where k is a fraction. So, it is a small, it can be 0.1, 0.2, so that is what it is now. So, with third harmonic injection, as we just saw, the peak value of the modulating signal is less than that of sine wave. So, it leads to the possibility that this Vm, that is the peak value of the sine wave, can be greater than Vp without pulse dropping. By pulse dropping, what I mean is, the value of MR star without the value of MR star exceeding Vp or going below minus Vp. So, if you look at in the previous case, that is with this MR star peak value being less than plus Vp or minus Vp, the highest value of Vm that you can get is greater than Vp. In fact, that value will be equal to 2 by root 3 times Vp when you take k is equal to 1 by 6 now. So, Vm can be greater than Vp. So, you can produce higher AC voltage that can with sine than what you can produce with sine triangle PWM, and k is equal to 1 by 6 gives the highest possible value, that is in this case Vm can be 2 by root 3 times Vp. So, 2 by root 3 is something like 1.15 roughly, and so you can get 15% greater sine voltage than AC voltage than sine triangle PWM with the same inverter having the same DC bus voltage. Now, actually you can this 1 by 6 is simply a factor being thrown at you, but this probably it is a good exercise for you to do this yourself, as I mentioned in my lecture on third harmonic injection also. So, what you are trying to do is, this is your k. You are trying to find out the optimum value of k, the optimum value of k that will maximize this value of Vm. So, subject to what constraint? There is one constraint that you have your MR star, this is your MR star, this MR star has to be less than or equal to Vp. Similarly, minus Vp should be less than or equal to MR star. Similarly, for My star, MB star and My star and MB star, sorry. So, you have this kind of condition to be satisfied by the 3 modulating signals. So, what you are trying to do here is, you are trying to optimize k, find out the optimal value of k which would maximize this Vm subject to this particular constraint. If you work out this problem, it is a very simple optimization problem. You will find that k is equal to 1 by 6 is the optimal value, which can give you a maximum possible value of Vm equal to 2 by root 3 times V peak. So, this is one value of k which is commonly used, which is 1 by 6. So, this is from the point of view of maximizing the AC voltage for a given DC bus voltage. You can get 15% higher AC voltage for the same DC voltage now. But again, if you try to optimize in from the harmonic distortion point of view, now you are trying to minimize harmonic distortion point of view. Previous studies have shown that k is equal to 1 by 4 or 0.25 is going to minimize the harmonic distortion. So, this is what you are going to do now. We are not yet prepared to do this kind of an exercise, but later after doing space vector PWM, we will develop some space vector based analytical methods for what you would call as analysis of current ripple. We would do some methods to analyze current ripple, and while analyzing current ripple, it will be possible for you to really work out something like this. With k is equal to 1 by 4, you might be able to see that you are getting a lower value of distortion now. So, this is what I have just tried to show on k is equal to 1 by 6. I showed it previously probably, and so now this shows that this is the highest value. So, here in this case the sine wave is now greater than 1, and that is actually equal to 2 by root 3, and you can see that the peak value of the modulating signal with common mode added is equal to 1. So, this is the highest, this shows the highest voltage, AC voltage condition at which highest AC voltage is obtained for the same DC bus voltage now. So, this is k is equal to 1 by 4. Now, you can see that here it is again the modulating signal is touching 1 stands for VP here, that is the peak of the carrier, and you can see that the peak value is a little lower now. In the earlier case the peak value was something like 1.15 something, in this case it is a little, it is clearly lower than that. So, with k is equal to 1 by 4 you can optimize the THD by minimize the THD, but you cannot really maximize the fundamental voltage that you can get. So, there is, as we will discuss later, conventional space vector PWM can achieve both, right. So, now we have looked at different kinds of modulating functions now. So, what we can see that the modulating functions can be continuous or discontinuous, that they can be continuous function of time. What do you mean by continuous and discontinuous? Function of, as a function of time. A modulating signal can be a continuous function of time or a discontinuous function of time. If the modulating function is a continuous function of time, you would call it as a continuous PWM scheme. If the modulating function is a discontinuous function of time, you call it discontinuous PWM scheme. We first saw sine triangle PWM. So, the sine triangle we also saw in for single phase as well as 3 phase inverters. These are continuous PWM methods now, and you can add even harmonics. In the case of sine triangle PWM for single phase inverter, we looked at both unipolar and bipolar PWM, and in unipolar we also added some even harmonics, though even harmonic does not give you the benefit of increasing the AC voltage that can be produced. In fact, addition of even harmonic reduces the AC voltage that can be produced with a DC voltage in the case of single phase inverter. In that sense, it is not advantageous. Whereas it is certainly advantageous when you talk of 3 phase, and in the 3 phase it is a third harmonic injection, which gives you a higher AC side voltage now. So, the sine and the third harmonic injection are continuous PWM schemes. So, sine is a continuous waveform, I mean this is a continuous function of time, and in the third harmonic injection what you are adding is another sine waveform just at 3 times the fundamental frequency. So, that is also a continuous function. So, the common mode function is a continuous function of time, and therefore, the resulting modulating signal is a continuous function of time in all the continuous PWM schemes. Sometimes you use modulating signals which are discontinuous functions of time. The common mode components will be discontinuous functions of time, which you will often do when you want to result in bus clamping. So, you want to resort to bus clamping, as we discussed in the previous lectures, and we will just look at it quickly now. So, in these cases the common mode signal is discontinuous, and when this is added to the sinusoidal modulating waves, the resulting modulating signal is discontinuous, and these are called discontinuous PWM schemes now. So, when you have bus clamping or discontinuous PWM, what it usually does, it clamps every phase to one of the DC buses over certain intervals in the line cycle, and usually it will be a 60-degree duration. You will find a phase clamped to the positive DC bus for 60 degrees, and you will find the same phase clamped to the negative DC bus for another 60-degree duration. Now, in this case the modulating signal is a discontinuous function of time, and as we have seen even in the last class, there are several modulating functions are possible. So, one of the modulating signal we saw was this 120-degree clamp, what is called as 120 PWM 1. So, you have, this is your sine wave, this is the R phase sine wave now, and you also see the Y phase and the B phase sine waves are shown here now. So, what you are doing now is you are extracting the common mode component from the sine wave itself. You take the sine wave whichever is highest and subtract it from Vp. So, for example, you subtract this and produce a common mode component, and your common mode component is like this now. So, and you add this common mode to all the 3 phases, what happens is the resulting modulating signal is like this, what is shown in the solid lines, red line, that is for the R phase modulating signal. You can see that the R phase is clamped for 120-degree duration, and similarly your Y phase is also clamped for 120-degree duration, and your B phase is also clamped for 120-degree duration. So, what happens here is it is never clamped to the negative bus. So, you can see that the top devices have a higher conduction loss than the bottom devices, and that is what we saw was a disadvantage in doing this now. Why is this happening? Well, because you are adding a common mode component whose DC value is not 0. That is what we would consider. So, its DC value is not 0. If you look at the other alternative for doing this, what you can simply do is you just go to the next step, that is you can take the other modulating signal. In the first case, you took the modulating signal which is maximum of the 3 modulating signals, and you subtracted from Vp. So, the difference between Vp and the maximum modulating signal, instead what you can take is the difference between the minimum modulating signal, the one which is minimum of the 3 and minus Vp, and you take that as the common mode signal, and this would be a common mode signal. You add this common mode signal, what you will get is as what you see here, like this is shown for the blue phase now. You can see that the phase is clamped continually for 120 degrees to the negative bus, phase would never get clamped to the positive bus. So, once again there is a uneven loading between the top and the bottom legs now. So, we have to get this clear, how to generate common mode signals which would result in bus clamping, nevertheless would not affect the symmetrical operation of the inverter. That is, all the 3 phases should be loaded to the same extent, and all the 3 phases should be both the top and bottom devices should be loaded equally. So, if you see, there are only 2 possibilities for clamping. You can clamp the phase which has got the highest modulating signal, which is most positive, or you can clamp the phase which is most negative, which has got the lowest modulating signal. Excuse me. So, it goes on like this. So, you can, if you want to clamp to the positive bus, then this is the modulating signal you can add. If you want to clamp to the negative bus, this is the modulating signal you should add now. So, your option is always this or that. At any point you have an option, you can either follow this or you can either follow this now. So, this would clamp a phase to the positive bus, this would clamp another phase to the negative bus now. So, your question is how do you go about doing that now, and there are several ways in which you can follow the 2 different waveforms. All the different bus clamping methods are different examples of how you are doing this now. So, if you look at this, certain rules here are the common mode signal must have a periodicity of 120 degrees now. So, if you see, this itself is periodic by 120 degrees, this is also periodic by 120 degrees now. You have a periodicity of 120 signals at the fundamental frequency. It must contain only triplet frequency components. So, this is natural. So, if it is 120 degrees means fundamental at the fundamental frequency. So, its fundamental frequency is 3 times the fundamental. So, it is like 150 hertz or 50 hertz modulation frequency. So, it will contain only triplet frequency components, and it must have 0 average value. So, the average value of that should be 0, that is, sometimes you must follow the positive common mode signal, sometimes you must follow the negative common mode signal, and you should go between the 2 such that the average value is 0. The average value at 0 will ensure that the loading of the top and the bottom devices are equal. So, it could follow the positive clamping and negative clamping common mode signals alternately. So, such that the value is 0. Right. So, one example is 60 degree clamp. What it does? It follows the positive clamping for 60 degree and it follows the negative clamping for another 60 degree. Again it follows the positive clamping signal for 60 degree and then the negative clamping signal during this 60 degree, and it clamps R phase for 60 degrees to the positive bus, B phase to the negative bus for 60 degrees, and then Y phase to the positive bus, R phase to the negative bus, and goes on like this now. So, this is what is called a 60 degree clamp in one example. So, you are following R and Y alternate, the positive and the negative common mode signals alternately for 60 degrees at the middle now. So, there is another, so this is just the extreme case, that is, I have shown here for a lower value of something like 0.8, I have shown Vm is equal to 0.8 now. Here I am taking Vm is equal to 2 by root 3. For that I am showing that this would be the resulting modulating signal. This is to show that 60 degree clamp can also work up to Vm is equal to 2 by root 3 Vp. So, you can have a DC bus utilization as high as that of the third harmonic injection with K is equal to 1 by 6. So, you can work, you can get 15% higher fundamental voltage than sine triangle PWM now, and you see that the common mode signal, this is how it looks now. So, a generalization of 60 degree clamp is the continual clamp PWM. What you do is you follow the positive common mode component for 60 degrees and the negative common mode component for another 60 degrees, positive common mode for 60 degree and negative common mode for 60 degree, and it can be positioned anywhere. In the earlier case it is positioned really at the center now, that is from the 60 degree to 120 degree. Here the phase is clamped, let us say from 30 to 90 degrees of the phase it is getting clamped now. It can be positioned between 90 to 150 degrees of the phase also. So, you can move around everywhere. That is, what happens here is, now you can follow this, like the middle 60 degree you can clamp, and then you can come over here for the middle 60 degree. You can go there to the middle 60 and come back to the middle 60. Now, there is no necessity that it has to be middle 60 here and middle 60 there. What you can also do is, you can follow this for 60 degrees here, and for the next 60 degrees, excuse me, and the next 60 degrees you can follow here now. Then another 60 degrees you can follow this curve, you can also follow like this now. That is one case. There is yet another case, you start, let us say you start from here, you follow the positive curve for 60 degree and you follow the negative common mode component for 60 degree and go about doing like this. So, these are all bus clamping, and in general you can start from any instant here and go on for 60 degrees on this and come and switch to the negative common mode, go for 60 degrees and do this now. So, this is what is called as continual clamping, because so these are different examples of what you are doing here, and in case of continual clamping what happens is the phase is continuously clamped for 60 degrees to the positive bus and then for 60 degrees to the negative bus and so on. Since it is clamped continuously for 60 degree, we just call it continual clamp, it is just a nomenclature. So, these are different examples of continual clamp PWM now. So, as I said, you follow the positive and the negative common mode signals alternately for 60 degree durations. This is what you do when you want to go for continual clamp PWM now. Let us go to the other thing of what is really called a split clamp PWM. Now, I am just taking one example as we will show here now. So, here what we are doing is during this 30 degree duration we are following the positive clamp. So, it is getting clamped to the positive bus now, and here what has happened is, so this is 60 degree and here I am just making sure that the common mode added is now such that they are clamped to the negative bus now. So, in this case what happens, the most negative value is Y phase up to this in this interval, and subsequently the most negative value is B phase in this interval now. So, in this interval the common mode makes sure that the Y phase gets clamped to the negative bus, in this interval the common mode makes sure that it gets clamped to the B phase gets clamped to the negative phase now. And after this what happens, you again move back to the positive common mode component now. So, if you move back to the positive common mode component, what happens is R phase is the most positive and the common mode component is the difference between Vp and the R phase voltage. R phase gets clamped to 30 degrees now. In the middle what happens, you are still following the positive common mode component. Now, the positive common mode component now basically comes from here. So, positive common mode component is the difference between Vp and this signal, and so the next phase Y phase gets clamped to 30 degrees now. So, here what happens, R phase is clamped to positive bus for 30 degrees and here again for 30 degree. This is between angle 30 to 60 degree and this is between angle 120 to 150 degree. Since they are clamped for 30 degree in every quarter cycle instead of 60 degree in every half cycle, here it is 60 degree in every half cycle, here it is 30 degree in every quarter cycle, and therefore, you give a name called 30 degree clamp PWM now. So, a generalization of this 30 degree clamp PWM is split clamp PWM now. And so, instead of 30 degrees and 30 degrees, this can be some gamma and some 60 minus gamma. So, they will add up to 60 degrees now. So, this is a particular case and this has not been very well studied till now. I mean, there are very limited studies on this. 30 degree clamp is widely known, but the generalization of 30 degree clamp name is split clamp is not so well studied now. I will come back to this when I deal with this bus clamping PWM from the space vector perspective also. It is split clamp PWM is not very easy to be seen from the 3 phase modulating signals, but it is much easier to be seen from the space vector point of view. So, I will just touch upon that when I deal with that in the space vector based PWM lectures. So, now, so this is all different examples of split clamping PWM. This is one case where this clamping duration is small here and long here, but the total clamping duration is 60 degree. This is the clamping duration here is long and here it is small, but again the total clamping duration is 60 degree now. So, it goes on now. So, just having a relook at the properties of the common mode signal. So, what we know is there are different kinds of common mode signals are there and you can add various common mode signals. That is how what we have been looking at. So, triangle comparison based PWM means what? You compare 3 phase modulating signals against a common carrier, and what is that 3 phase modulating, what is a modulating signal? It can be sinusoidal or it can be sine with some common mode signal added. So, we just have to be clear as to what kind of common mode signals should be added. So, you have Vm sin omega t. I am not writing down the modulating signals for the other two. Now, you are adding common mode. The same common mode is added to My and Mb also to produce My star and Mb star, which I am not giving here now. The common mode added should be small. It should be small such that the resultant MR star should not it does not go beyond plus Vp or minus Vp. So, minus Vp less than or equal to MR star less than or equal to plus Vp is one of the constraint. So, the common mode amplitude has to be small enough such that this constraint is met now. On top of this, what should you do? The common mode component must have a fundamental frequency equal to 3 times the modulating frequency. That is, the common mode component's periodicity should be 120 degrees of the fundamental now. Only then it is what is added is common to all the 3 phases now. So, this is another condition, and this condition naturally means it has only the triplet frequency components like 3, 6 etc. and usually this common mode component many times will have a half wave symmetry. Let us just look at that. Let us say you look at a common mode point where it is clear. So, this is a common mode component now. So, this dashed line is common mode component, and you can see that it has got a 120 degree periodicity. The periodicity is periodic over 120 degrees now, and you take this half wave and this half wave, you can see that is symmetric now. That is the common mode component value at theta, and its value at it's 120 degree and its half period is 60 degree. Its value at theta and its value at 60 plus theta are the negative of one another. So, this waveform has half wave symmetry. This waveform itself has no even harmonics, and therefore, what you will find is it will not have 6, 12, 24 etc. It will have 3rd, 9th, 15th, 21st etc. So, because this is a waveform of fundamental frequency of whose periodicity is 1/3 of the fundamental, and so therefore, it has, and it also has half wave symmetry. So, it has harmonics of the order 3, 9, 15, 21 etc. And then what you have to do to ensure equal loading of top and bottom devices, you have to make sure that the average value of common mode component should be equal to 0. This is again one factor that you have to. Subject to these constraints, basically it is possible for you to generate several kinds of common modes. The only question is, what is the advantage in adding a common mode? One advantage would be that some common modes can give you addition of like increased DC bus voltage. Sometimes they can give you a reduction in the pulsating torque and so on and so forth. So, what I am trying to say is, you can examine some more common mode signals like this. These are they are possible, and what I have indicated are all popular examples and which have been useful in some particular sense or the other now. So, if you want to go into some more investigations, you just have to make sure that these are met. So, that this would basically ensure that you are adding a common mode signal which would not take the inverter into over modulation, which will keep this still in linear modulation. It will not go into what is called as pulse dropping, and it will make sure that all the 3 phases are loaded equally, and it will make sure that the top and the bottom devices are loaded equally, right. So, just some general remarks about the performance of continual clamp and split clamp PWM. Of course, at this point of time we have not developed the necessary analytical tools for us to be able to analyze and compare continual clamp PWM and split clamp PWM. So, it is more kind of an assertion that I am making now, and at during when we are in a position to analyze the current ripple and etc., we will be able to probably later on we will try and develop some analytical tools. During that time, it will be possible for us to make better sense out of the claims that are being made here now. Nevertheless, these are facts which have been established and discussed in the literature now. So, if you take continual clamp PWM and split clamp PWM, where continual clamp, a phase is clamped continuously for 60 degree duration in every half cycle, and in split clamp PWM, a phase is clamped for some duration gamma and 60 minus gamma, which so they add to 60 degree in a particular half cycle. So, it is clamped for some duration gamma in the first quarter and 60 minus gamma in the second quarter. So, the clamping durations is split into 2, gamma and 60 minus gamma, and hence the name split clamp PWM. So, what has been seen is continuous clamp PWM reduces inverter switching loss significantly at high power factors. That is, let us take one continual clamp PWM, the simplest is 60 degree clamp PWM. So, you take here now. So, what happens here, R phase is not switching at all here, and what is the R phase fundamental voltage? It is simply proportional to this now. Now, let us say the load is unity power factor, the AC side load is a unity power factor load. So, the current will also be in phase with the voltage now. So, what happens when the current is at its close to its peak, the phase is not switching, and the switching loss, every time you turn on and turn off a device, there is going to be loss. And what does that loss depend on? One thing it depends on is the DC bus voltage. It is almost directly proportional to the DC bus voltage, and it is also roughly proportional to the current that is being switched now. Therefore, let us say when now this is the voltage waveform, let us also assume this to be the current waveform with the unity power factor load. If you are switching this phase when the current is very low, the switching energy lost is very low. On the other hand, if you are switching the phase here when the current is high, the switching energy lost is high. Now, if your load is unity power factor load, this 60 degree clamp PWM makes sure that you are not switching that particular phase when its current is very high, and therefore, it results in a substantial saving of energy that is lost, and therefore, you can say for unity power factor cases or power factors close to unity, the 60 degree clamp is very good, is a good option. It reduces the switching loss now. So, you can say that here the clamping is between 30 to 90 degree. Let us say when the load is slightly leading, so the current is leading the phase voltage. Again, so this kind of 30 degree clamp PWM where the clamping is from 30 to 90 is going to be advantageous. Now, let us say if it is lagging load, as it is the case in the case of induction motor drives, you can simply clamp between 90 and 150 degree. In an induction motor drive, since it is by and large, this is a good option, this PWM method. Why? The phase voltage is like this and the phase current will lag the phase voltage. So, the phase current will have its peak somewhere in this region, and in this region the phase will be clamped, and therefore, the switching energy loss is low. So, from switching loss point of view, this method can be a good method for motor drives. So, you can actually place the 60 degree duration anywhere you want within the 120 degree interval now. So, you can do it precisely according to the power factor when the power factor is very high. When the power factor angle is between minus 30 to plus 30 degree, you can make sure that the phase is clamped whenever the current is around its peak now. So, these are very good for high power factor loads. So, that is the claim that is being made here. Continual clamp PWM reduces inverter switching loss significantly at high power factors. On the other hand, split clamp PWM reduces the switching loss considerably at low power factors. This has been reported in some recent papers, including the reference that has been mentioned here. So, what happens in split clamp PWM is, let us go to the 30 degree clamp. Now, here what happens, R phase is clamped here and Y phase again R phase is clamped there. Let us say you consider 0 power factor load. So, the load voltage is 0. In case of 0 power factor load, the current is going to be at its peak. So, the load current is going to be at its peak now. So, from the peak, let us say it is falling down to 0 like this. So, it is clamped. When it is clamped, the phase is clamped when the current is between 0.866 times the peak to 0.5 times the peak. So, whenever the phase current is between 0.5 times the peak value and 0.866 times the peak value, it is getting clamped now. So, this results in a substantial amount of saving. Though you are not able to clamp the phase exactly when the current is going through the peak, you are able to clamp it whenever the current is between 0.5 times the peak and 0.866 times the peak, and therefore, this is able to reduce it some amount of switching energy loss. So, this is I am just trying to say why this is true. Split clamp PWM reduces the switching loss considerably at low power factors. So, this has advantage at high power factors and this has advantage at low power factors from the switching loss point of view, because bus clamping PWM itself is one idea that you often use to handle this issue of switching loss now. The next question is about distortion. If you compare the two in terms of harmonic distortion, split clamp PWM leads to lower harmonic distortion than continual clamp at any given modulation index. You take some value of fundamental voltage like 80% of the 6 step voltage or 70% of the 6 step voltage. You can use split clamp PWM, you can also use continual clamp PWM. What you will find is split clamp PWM leads to lower harmonic distortion than continuous clamp PWM is what you will see now. Again, at this point we do not have the necessary analytical tools in place to understand this particular statement in any greater detail. Nevertheless, this is a fact. I am hoping that at a later date, after we have discussed space vector based PWM and after we have discussed how to evaluate line current ripple etc., we would be able to revisit this question and understand why split clamp PWM leads to lower distortion than continual clamp PWM. Now, this for further references here, this particular paper, it is basically more on advanced bus clamping PWM methods and it is not so much on bus clamping PWM itself, but still it has certain details about bus clamping PWM. So, I would suggest this particular reference which I have also given in some earlier lectures, D. Zhao, VSS Pawan Kumar, Hari, Narayanan and INR. This is space vector based hybrid pulse width modulation techniques for reduced harmonic distortion and switching loss, published in IEEE Transactions on Power Electronics in the March 2010 issue now. So, this is what we have essentially. So, this has further references on this now. So, what we would be doing in the subsequent classes is we will be going into space vector based PWM now. So, what we looked at right now is different kinds of common mode signals that really can be added to the 3-phase signal, and our basic thing has been to move over to let us say what we looked at from the previous picture, that is we looked at a particular way of modulation, that is triangle comparison based modulation. What we looked at is how the way of producing the PWM signals by comparing 3-phase modulating signals. So, every phase has got a particular modulating signal and it is compared against a triangular carrier, and by this triangle intersection you are producing the PWM pulses now. So, this is something called per phase approach. For every particular phase you are having a particular modulating signal. The alternate approach is to look at all the 3 phases together, what I would call as space vector PWM. You look at, we will next class what we will do is we will go about defining what is called as a space vector, and then we will define what is called as space vector transformation. So, that is how you can transform 3 phase voltages into what is called as a voltage space vector, and now based on the space vector idea we will develop modulation methods. So, I would say there are 2 possible approaches which are commonly used for producing PWM generation. One very popular approach is triangle comparison PWM. So, this is been there around for about 3-4 decades now, longer than that, and space vector based PWM is relatively newer. It you could say that it started being used from the middle of 80s or so, and that is space vector based PWM. So, that is what we will be discussing in the next class now. In this triangle based comparison based PWM is originally sine triangle PWM, and then there are variants of sine triangle PWM, and sine triangle PWM you can say it had its origin in the modulation theory. That is when you kind of modulate 2 different signals, what happens, sine modulation. Similarly, you can look at sine triangle modulation, it started from there. And the space vector theory on the other hand, I would say had its origin in generalized machine theory. That is, you can start looking at revolving space vectors. We are familiar with time phasors, right. That is, you have several quantities which are sinusoidal, like the signals that we use sometimes are sinusoidal signals. And whenever a quantity is sinusoidal, you can represent it as a time phasor, you express it as a revolving phasor. Now, you can also think of revolving vectors, I mean in space. For example, you take a 3 phase machine, and the 3 phase machine's MMF is revolving, right. So, that is an example of a space vector. So, now we are having space triangle comparison based PWM. Similarly, we will be going into what we call as a space vector based PWM. That would be an alternative approach now. So, in the next 3 or 4 lectures we would look at what is space vector based PWM. That would be the next module that we will be dealing with, and subsequently what we will be trying to do is we will trying to kind of compare the space vector based PWM and triangle comparison based PWM, and we will be getting trying to get a good picture of what exactly we want to do now. So, meanwhile, I just go back and I just give you this reference which I just indicated to you now, and I hope this particular lecture was helpful for you, and hoping to see you during the next lectures. Thank you very much.